Okay, I'm in my dining room and we'll move to my living room trying to record about limits. Limits, this is a strange new world. You're going to think of playing a game of sneak attack where you slowly creep up on somebody. You're going to approach your subject very stealthily. You want to make sure that you can get to get closer as though you were going to nab them and attack them, but you don't get to. This is the world of limits. This sneak attack will occur from what they call below or the left and above from the right. So, for example, if you want to sneak up on x equals 2 from the left or below, you might start at 1.9 and go to 1.99 and go to 1.999 and 1.99999 and on to 1.99999999999999999999999999999, but you're never going to get there. From the right, that is above, you're going to maybe start at 2.1, go to 2.01, then to 2.001, and then to 2.00001, and then you keep on going in this pattern to 2.000000000000000000001, but you never get to 2. You just slowly make your way creeping towards x equal 2, but you never actually get there. The limits, the informal definition. If x becomes arbitrarily close, and by arbitrarily, that's what I was demonstrating when I said 1.99999, 2.00001. You're getting very close, but you're not actually there. To a single number, L, as x approaches a particular number value of c, such as 1.999999 or 2.00001 from the other side, then the limit of f of x as x approaches c is L. It's written LIM x arrow c, which is read the limit of f of x as x approaches c, or the limit as x approaches c of f of x is equal to L. Now, when we talk about approaching from below or from the left, we write it as x approaches or x arrow c with a little negative sign where you would have an exponent. And from above or from the right, you would have a little plus in the exponent position, because as you approach your number c, it will always be a number. It will not be 2 squared, it would be 4. And if the number is negative or positive, that would be indicated in front. So I could be approaching -2 from the left, and if I were, this would mean that I would have -2 left, or -2 from the right would be -2 right. So notice the exponent position is reserved for telling us if we're approaching from above or from below. Moving onward. Okay, limits exist. You're continuous. Notice I've given you several graphs here, horizontal, oblique, a couple of curves that we go through. The left side, just put your hands on the point. Wherever your left hand goes is the left side, the right side, a lot like how we did in behavior, folks. So the limit as x approaches 2 from the left in the first picture, and the second, and the third, and the fourth is 5. The limit as I approach 2 from the right, notice, here's from the left, I'm approaching, from the right, I'm approaching, from the left, I'm approaching, from the right, I'm approaching, from the left, I'm approaching, from the right, I'm approaching, is going to be 5. And the limit, therefore, since these two are equal, that's how we determine that a limit exists. Remember, the definition says that we have to approach some arbitrary number, and so we have done so. The limit from the left equals the limit from the right. And so my limit is 5, and my function value is 5. Now notice, I call the limit is when you're getting near. That's what closer means. That's what approaching means. And I call my function value at. So this is your at. This is your at. This is your at. This is your at. Your limit says what y value am I coming toward? Well, here I'm coming towards 5. I'm coming towards 5 because I'm always 5. But here I might have been 4.9, 4.99, 4.9999999, and maybe I was 5.1, 5.01, 5.00001. You don't know, but we're approaching. So what a limit means is what value are you near? When I plot a point, that's an at, that's my function value. And notice when the limit is equal to the function value, we call that continuous. That's how we connect up to the notes that we shared with you earlier. Now, limit can exist when we have a point discontinuity, a hole, that is, it will be called removable later. Notice there is no ordered pair. A point is absolutely just missing. No ordered pair, point missing. No ordered pair, point missing. It's just not there. And so when I look at all of these, it's similar to your other graphs. As I approach from the left side, this one's always 5. From the left side, this might have been 6, then 5.9, then 5.1, then 5.01. As I approach from the left here, maybe it was 4.9, 4.99. As I approach 2, that's supposed to say 2. Don't ask me why it looks like a 3, folks. It's really a 2, see? When I approach 2 from the right, now here it's always 5 because it's horizontal. Nobody cares. But from the right side, 4.9, 4.9999. From the right side, 5.1, 5.00001. That's where I'm going. And so the limit exists because the left side matches the right side. And so I say that my near, when I get near 2, I'm near 5. That's what a limit means. Near 2, I'm near 5. But notice at 2, I'm undefined. There is a point missing. When these two are not equal, you always have a point discontinuity or a hole. Now, continuing on with holes, what happens when I have the point pops out and it's elsewhere? So notice my actual function value is at 6. My actual function value is at 6. But we're discussing what's going on at the graph as I approach 2. As I approach 2 from below, I'm going to 5. Approach 2 from above, I'm going to 5. From below or the left, I'm 5. From the right or above, I'm 5. And so the limit exists because both sides are near 5. And so the limit says when I'm near 2, I'm near 5. But at 2, I'm 6. Again, they're not equal, and this describes that a point is missing. Now, let me reiterate what I've been saying. The limit exists if and only if the limit from the left, as I approach my number, is equal to the limit from the right. Now, I want to go back and move to what we discussed in your first set of sheets that I sent you 4 pages of pictures. The continuity definition says if the function value exists, the limit exists, and the limit is equal to the function value, then we're continuous. Notice function value, f of x, has absolutely nothing to do with limit because I ask if the limit exists. I ask if the function value exists. Those are 2 separate things. But it has everything to do with continuity. Because in continuity, the limit must equal the function value. The limit must equal the function value. Notice when we had a hole, the limit doesn't equal the function value. The limit doesn't equal the function value. But When we're continuous, the limit does equal the function value. Now I'm going to cover up the camera as I move from my dining room into my living room, and on the old piano we will continue. All right, limits does not exist, abbreviated D&E. We have the jump that we talked about on the worksheet. And in the jump, you can see that this jumps. They're not connected at all. They're actually one of these open circles is above the other open circle, a jump, because you have to have a graph connected to the open circle. If it's not connected to the open circle, we don't care about it. Okay, so you'll notice that as I approach, because I did horizontals here, from the left side I'm 5, from the right side I'm 6. Notice I get two different numbers, real numbers, different values. They're not equal. That always defines a jump when you read a table or you're looking at a graph or some numerical chart. A table. So this is D&E, and notice I don't have a closed circle anywhere, so there's absolutely no function value. For the next example, notice I put in a function value at 5, but again, I have a point above a point. One's closed, one's open. That's a visual definition of a jump. The limit from the left is approaching 5, maybe 4.9, 4.99999, never quite gets there. The limit from the right will just be 6. I made it horizontal, but again, I have two different numbers. They're not equal to each other, so that's a jump. So that means the limit doesn't exist, and the function value is 5. Like, who cares? The function value only matters when you're trying to decide if you're continuous or a whole. The third example, because some of you absolutely need one of each, notice I put the ordered pair with the 6. In this one, the limit from the left is coming in, maybe 5.1, 5.0001. The limit from the right is maybe 6.1, 6.01, 6.0001, but at any rate, I get 5 and 6. They're real numbers. They're not equal. That's the definition of a jump. The ordered pair 6, it doesn't help me out. Notice that there is no near because one's on one side, one's on the other side. The last example of the jump is what if I put the ordered pair somewhere totally by itself. Notice those are all vertical to each other. When I come up and down, I could put a vertical line through it to draw the graph. That's how we figure out a jump. So from the left side, I'm coming in on 5, maybe 5.000001. I made this one horizontal at 6. Again, two different numbers. They're real. They're not equal. It's a jump. And the function value 7 is elsewhere. Now, some things we need to know. To be a jump, you're going to get a number from the left and a number from the right. These two numbers can never be equal. If these two numbers are real and they're not equal, then that is how we determine that you have a jump both from a table. Numerically, graphically, analytically, table is the same as numerically. Analytically is algebraically, and we can do it graphically. When we write the stuff down, that is when we are doing the fourth prong of the presentation. Now, I want to review what it means to be a vertical asymptote. When you have a vertical asymptote, the y value is called unbounded. That's the term they'll use in college. It doesn't exist. What you can do is describe the y behavior. Here, the y behavior is heading towards positive infinity, and here the y's are sliding down to meet Satan at negative infinity. So, when we say that we are heading towards positive infinity, that means we're unbounded, or heading towards negative infinity, that's unbounded. These really mean there is not a limit because there's not a real number there. And remember, the original definition tells me that the limit from the left must equal the limit from the right, and we told you it was a real number L. But Positive infinity implies D and E, negative infinity implies D and E, but we're going to use plus infinity to describe behavior and negative infinity as answers. Okay, the limit does not exist, and we call it infinite or vertical asymptote or unbounded. Again, your college professors love unbounded. That's all I learned when I was in college. AP tends to use a lot with infinite and vertical asymptote. So I gave you a picture. Notice the left side is heading to negative infinity. The right side's heading to positive infinity. They're not equal, the infinities, but the main thing is they're not a real number, so that would mean D and E. And so near where D and E, notice I did not put an ordered pair on the asymptote, so it's undefined. Now I'm going to put the ordered pair on the asymptote. The limits are still negative infinity, positive infinity from the left and right. The limit is D and E, but the function value is 1. Again, what good does that do us? Now down at the bottom, I make a graph where both of the sides point towards heaven. And so the limit as I approach 2 from the left is going to positive infinity. The limit as I approach 2 from the right is going to positive infinity. These are equal, but not a real number. And if somebody asks you, does the limit exist? No, it doesn't. But if you have a multiple choice answer and they ask you, what is the limit? And positive infinity is there, you're going to pick it over D and E because that's what mathematicians have chosen to do. When you're approaching both sides positive infinity, we will say that the limit is positive infinity. We will describe the Y behavior. There is no ordered pair, so it's undefined. So now I did another graph showing you that there is an ordered pair on the graph, and now we're heading down towards Satan. And so the limit on both sides is heading to negative infinity. Technically, it's D and E, it's unbounded, but the negative infinity describes the direction, and so these are legal answers. Because they're both the same, infinity, we write this answer as negative infinity. Again, this means D and E, but it's a better answer than just D and E. Mathematicians say negative infinity means D and E. Again, if it was multiple choice and D and E was a selection and negative infinity was a selection, you would have to choose negative infinity. They only use D and E when the two quantities don't match, like in jumps and when you're going to different infinities. Again, I give you an ordered pair, but it didn't do anything. So remember, plus infinity and minus infinity mean D and E, but represent Y behaviors. Hence, these are descriptors, not actual values. When applicable, you are required to write positive infinity and negative infinity. Now, the last form of a discontinuity where the limit doesn't exist is oscillating. These are tough to graph. We'll do one in another video when I show you on the calculator. It's kind of like doing the graph of 1 over cosine x between -1 and 1 or something like that, and you'll see we'll get it there. But oscillating says it's jumping from one y to another. So in here it's going like from here to here to here to here to here to here. It can't make up its mind. It's not nice and connected like it is over here. It's just, it just looks like it's doing one of these and you're going to say, ah, it looks like an accordion squashed in. These never are connected. So all the limits are D and E. And they're unless I give you a piecewise function, the function value is always undefined. Now this covers the notes that you have from 12.1 on 12.1, 12.2, I think, through page 5 or so. The next video that we would be doing or sending you information on is how you could actually do the table sheets and read some of the graphs that we gave you for the first 3 sheets.